Okay, let's get started then. Okay, are there any questions before we get started? If not, let's share screen.
I had a quick question. I was
Sure.
just curious, roughly how long you think the exam will take. Is it about the same length as one of the homeworks, or a little shorter, or a little longer?
I would say it's about the same length as the homework, a little longer maybe. The question would be a little bit more difficult than the homework. Okay, so a little bit more difficult than homework, I would say. Okay, but you get about the same number of problems as the homework, 3 to 4 questions. Okay. But the reason why it's more difficult than the homework is because I want you to learn something during the take-home exam. So after take-home exam, you feel good that you learned something, or you feel bad that you learned something, or you feel bad that you can't do the take-home exam. But hopefully you will feel good that you can do it and that you have learned something new. Okay. Let's see, let's get started. Let me see. Now, today I'd like to talk about transmission lines. Transmission lines are some of the most important technologies in electromagnetics. The reason why it came about is because of telegraphy. You know that in olden days, let me forward my laptop so that I can more easily write. Look, that's around 1800s. Okay, if you recall that during that period, we have Faraday's law. And then we have Ampere's law. And then by 1865, we have Maxwell's equations. Okay, and people like Oliver Heaviside, he was really good with the theory of transmission lines. Okay, he was really good with the theory of transmission line. He was able to explain many things in the transmission line of telegraphy technology, or telegraphy technology, using his own knowledge. So in general, a transmission line consists of 2 pieces of metal, such as this one. Symbolically, it can be written like this, but physically, it might be consisting of something that looks like this: 2 pieces of metal, arbitrary shape, as long as you have one that's positively charged, and another one is negatively charged. And the two pieces of metal can be looking like this, and this we usually call a strip line. And then the two pieces of metal can also look like this. And then it is a coaxial cable. Okay, a coaxial cable. And then there will be positive charges on the inside and negative charges on the outside. The outside is usually grounded. Or you can have two pieces of metal, like what you often see, the power transmission line is something like this. If some of you have very, very old television, some of these lines used to come to our home as a transmission line for home television. But I guess most of you are too young to see that, okay? But the two pieces of metal do not have to be parallel. They can actually be twisted like this, called a twisted pair. And you can use that to carry signals as well, because they consist of two pieces of metal. Does anyone of you know why a twisted pair is advantageous compared to, say, if you have just two pieces of wire? You just connect them like this.
Probably the length.
The length is one thing, but there's another thing that's very, very important.
The signal should always be 90 degrees offset from each other.
You didn't say it elegantly. Maybe somebody can say it elegantly. Why is a twisted pair important? There's no phase shift. There's hardly any phase shift because this also works for very long wavelength signals. So saying that they're always 90 degrees apart, it's not quite correct. Okay, you're almost getting there, but not precisely there. So does anybody have a more articulate way of saying why a twisted pair is preferred? Anybody? Well, it is usually due to isolation. So if this pair of wires are exposed to, say, a magnetic field like this, a low frequency B field, okay? Then we know what magnetic fields do. If they're time varying, they induce voltages in these loops, okay? If go through this, if you have a source here, if you have a load here, then if this magnetic field goes inside, the dB/dt effect in Faraday's law would cause a voltage to be induced. It causes a voltage to be induced in these loops. And if you have twisted pairs, then the voltages are in series opposition to each other. The one that's in this loop will give rise to a voltage that is negative to that and negative to that. In total, the twisted pair give rise to coupling to magnetic field that is greatly diminished. Okay, diminished the coupling to magnetic field, and hence you have better isolation. So that is the most important thing about twisted pair. But that was just a digression, okay? I actually want to teach you about transmission line theory, but I want to emphasize that even though the symbol for transmission line is something like this, the two wires do not have to be parallel, okay? You can see this from a circuit theory analysis. And let's try to derive the very simple equation for governing this transmission line. And you can first think of two pieces of metal as being a concatenation of pieces of small sections. You break this piece into small sections like this, you concatenate them. And then when you look at each section, you try to understand the physics that you see. So the physics that you see is that these are metal. So there will be charges building up in this metal. As a consequence, there will be electric field going like this, okay? And then some of these pieces of metal, you might have negative charges like this, okay? And then the electric field will go like that. So this is something we call capacitive coupling. Okay, but moreover, if you have a piece of current or a current flowing in this piece of metal, that will give rise to magnetic field. You know that if you have a piece of metal and if you pass current through that by Ampere's law, let me see if we get Ampere's law correct. Yeah, Ampere's law, the H field will look something like this. Okay, so as current flows in this piece of metal, they give rise to magnetic field. Okay, the magnetic field gives rise to stored magnetic energy. You have already learned from Poynting's theorem, there's something called the stored magnetic energy, which is proportional to half mu h squared. Okay, is this stored magnetic energy that gives rise to inductance. Okay, and then the stored magnetic electric field energy gives rise to capacitor. You can think of a capacitor being an electric energy storage device, whereas the magnetic field is the magnetic field energy storage device, and so on. So now that we know the physics quite well, let's go ahead and analyze the mathematics behind it. So let's try to derive the Telegrapher's equation. Okay, how does the Telegrapher's equation look like? Let's do a very simple derivation. Since we are confining ourselves to very small pieces of element, okay, small pieces of elements, we can use simple circuit theory to describe what happens there. So if we imagine a current flowing in this inductor, we can apply circuit theory or Kickoff Voltage Law to this inductor and write down an equation. And that equation should follow that of the, let me go to the next slide. And hopefully you can still see this, this picture on the left. Okay, so that inductor that I just described, sorry, there should be a T here. Doesn't work well. Refuse to erase today. What happened? Why does it refuse to erase today? It does. Okay, the inductor would follow this IB relation of an inductor. Okay, we know this from our circuit theory course. But we have an inductor here, but the inductor that we have is the line inductor times delta Z. Okay, if you look at this piece of element over here, the inductor is actually L times delta Z, where L is inductance per unit length. Okay, then you can actually write down the Kickoff voltage law for this very small segment where you have the current I flowing in like this, and then it will give rise to a different voltage at different nodes. Okay, here we have V, and over this side we have V plus delta V. Okay, the voltage drop then is equal to this voltage minus this voltage, and then we have V minus V plus delta V is a voltage from here to here, okay? And that voltage drop must be equal to the inductance times the time rate of change of the current, okay? And I'm going to assume that the current I is going to be a function of Z and T. That is, the current is not going to be a constant anymore. Okay, the current is going to change from segment to segment along this transmission line. So I'm going to write the current not being a constant, but changing as a function of Z. So I will have to change this to a partial derivative. Okay. And then you can figure out what V minus delta V is. V minus V plus delta V is, this will be just delta V. So we arrive at an equation that says that minus delta V is equal to L delta Z partial I ZT partial T. Okay. And then in the limit, when you make delta Z very small, limit when you make delta Z being very small, this equation can become, like you divide by delta Z, you get this equation being L partial I partial T. Okay, these are all approximate because we're using calculus concepts here. And then this will become partial V partial Z. Okay, so we have partial V. V is a function of Z and T as well. Okay, this is the first of the two telegraphist equation or telegrapher's equation. Then we can do the same thing with the current. The current, if I were to look at the current is going to leak out and along each of this. So the current at the two ends of this node will be different. And if you write down Kickoff current law for this node, you can easily show that, well, the change in the current, or the current that goes down to the third branch, is minus delta I is equal to I at ZT minus I plus delta I, okay? So if you write the Kickoff current law at this node, you have I minus I plus delta Z, which is the difference of these two currents, should be equal to the current going down the third branch, okay? So if you write that down, you will have this. Again, taking the calculus limit, okay, taking the calculus limit, this should be equal to C delta Z, applying the BI relationship for, let me put the VDT here, okay? So that should be equal to the current going down this branch. The current going down that branch is given by the capacitance per unit length times delta Z times this, because we know that I is equal to C naught dV dt in the capacitor, okay? But instead of C naught, we have an incremental capacitance given here, and assume that delta Z square is very small. Okay, delta Z square is very small because we have the voltage at this point is V plus delta V, or V plus delta V, sorry. This should be delta V. Let me erase this and write this again, delta V. We are assuming that the terms that involve delta Z times delta V is very, very small. Okay, very, very small. So we can drop the product of the very, very small term, okay, and rewrite this equation as minus delta I over delta Z being equal to C, and then I'm going to drop this term out because it's so small compared to the other terms. Partial V ZT partial T. And in the limit when I take delta Z goes to 0, then I have this partial I ZT partial Z is equal to C partial V ZT partial T. Okay, so this equation together with this equation form a pair. And that pair of equations is known as the telegrapher's equation or the telegraphist equation. Okay, any questions so far? So this, I hope, is a revision for many of you, because many of you have had the transmission line theory course as an undergraduate, but even if you don't have the background of transmission line theory, this is quite easy to learn because this is circuit theory, not electromagnetic theory. Okay, so the Telegrapher's equations are given by this. Okay, and you can convert them to wave equations by just differentiate this with respect to Z1, and then you will have differentiate this with respect to T1s, and you notice that the right-hand side will have a term that looks like partial square, partial T, partial Z. But then you can replace partial B, partial T, partial Z with this one. The right-hand side of this will be L partial I partial T squared. And what you have then is that you have an equation that looks like the 1D wave equation, partial I partial Z squared minus LC partial square I partial T squared is equal to 0. And you can do the same thing for the other way around, keeping V as the unknown or the important variable. Then you will have this other equation. Okay, can anybody remember what these equations are? What structure do you have? And it correspond to some equations that you have learned before. Anybody? What equations are this? I'm not hearing anything. I hope my microphone is working. Can you hear me?
Yes.
Okay, I can hear you now. When somebody talks, I can hear something. Otherwise, it's a dead silence. And I was quite afraid that my microphone is not working. So what are these equations? Something that you have learned before in the course. Anybody? Well, when we studied Maxwell's equations, we have something like this. Maxwell's equation looks something like this. Mu partial H partial T, which is Faraday's law. And then we have Ampere's law, which looks something like this. And Maxwell's equations are too complicated to solve. So we did something clever. We say, why don't we let X be just something like this? And then when they plug that in, and then we find that we have a very simple equation for E, EXT. We have something like this. I don't know if you remember that. Sorry, should be C here. Should be C here. X here. Can anybody remember what this equation is called? We did that in Maxwell's equation. We say it was a triumph of Maxwell's equation that we see something and we derive something from it. What is that equation called?
This is wave equation, but I was thinking that you were asking about hyperbolic equation or stuff like that.
Oh no, not such advanced concepts. Those are too advanced concepts for this class. Okay, these are the wave equations. Okay, the wave equations. Well, in the wave equation, maybe I have my wave equation written wrong. I just remember that. This is not right. Okay, this should be just mu epsilon. Okay, so wave equation can also be written as, yeah, you're thinking too far ahead. These are also called hyperbolic partial differential equations. Okay, but I don't need you to know that for this course. So the wave equation can also be written in this manner. where the velocity of the wave is 1 over square root of mu epsilon. Okay. So if you compare this transmission line equations, they can be cast into a form that looks like the wave equation. And what is the velocity of the wave on this 1D wave equation for transmission line? If you were to draw the parallel between what you have learned before, what would you say the velocity should be?
It's 1 over square root of LC.
Very good. So it should be 1 over square root of LC. Okay. If you have problem remembering this, here is the line inductance. It is measured in terms of Henrys per meter. Okay, so it's actually in terms of Henry per meter. This is like capacitance, so it actually is in terms of coulombs, right? Charge is coulomb. Did I say that right? I might be remembering this wrong. Okay, so the capacitance, what is the unit for capacitance already? Can somebody remind me?
Farads.
Farad, right, Farad, yeah, it's named after Farad, very good, okay, not Coulomb, I get all these famous people's name confused. So capacitance is measured in terms of farads. So it's farads per meter, and then since it's a line capacitance in terms of farads per meter, the inductance is in terms of Henry per meter. So it's very much like this mu and epsilon that we have learned. They have the same unit. And so when you plug that in, you get the same velocity. Okay? Same unit for velocity. Any questions so far? Well, very interesting thing, but there's one more thing that we can infer from this wave equation, which is that if you have a voltage and a current on the transmission line, okay, we say that if you have a transmission line, we can define voltage as a function of time and space, and then the current is a function of time and space, and they satisfy the wave equation. So we already know that the wave equation has solutions that look something like this. Let's assume that we have a one-way traveling wave, that the wave equation has something that looks like this, okay? It's just a positively traveling wave, and then we know that the current must be also positively traveling, but with a different amplitude. Okay, but these two are actually related to each other because we see that they must satisfy the telegraphist equation, which we had in the previous slide. Okay, the telegraphist equation. When we plug this into the telegraphist equation, if you plug into, say, dV dz here, okay, dV dz, then you can find that dV dz is V naught F plus prime Z minus Vt, right? And then you have to put a minus sign here. And then that should be equal to L partial I partial T. Agree? According to the telegrapher's equation that I have up here. Then you plug the right-hand side in, and then you would have this being equal to, if you differentiate this with respect to T, you know how to use the chain rule to differentiate this, okay? So it's L, and then you will have to have, you have to have a minus V coming out using the chain rule, I naught F plus prime Z minus Vt, right? You have this coming out. And then you have this equation being equal to that, but what is V equal to? We just have learned what V should be. V is 1 over square root of LC, okay? And then if you plug this in now into this equation, you have this relationship, and you will find that I naught VL is equal to V naught, or that V naught over I naught is VL, which is 1 over LC times L, which is equal to square root of L over C, okay? So if you use this relationship, you'll find that always, that the ratio of these two currents, okay, because the two functions F will cancel out, you will have this being equal to that, and you always get this. This is called Z naught, which is a very important number in transmission line theory. This is called the characteristic impedance. Okay. And let me try to ask you something else. In space, we have eta. Eta is mu naught over epsilon naught. Okay. And that is inductance per unit length divided by capacitance per unit length. Do you remember what the name for this eta is? What do we call that for free space? Does anybody remember that? Eta is, what is the name for it? At least you should know the name. I hope that this is not the course for just learning names, but you have to have the same name so that you can communicate with other people. What is eta called in this course? Anybody? Well, let me see if anybody is around. Oh, I still have 16 people in the class. Okay, so you're still around it. This is called the intrinsic impedance. And something that you should commit to memory is that this is about 377 ohms in free space. Okay, but this is something else. Okay, you will find that this does not have to be 377 ohm. It can be anything. There's a wonderful part about transmission line theory. You can have a wave traveling in this thing. The velocity is given by this. Okay, you can change its velocity. You can also change the ratio of the voltage to the current. And you will learn more about that in a little while. Okay. Any questions so far about transmission line theory? The next thing we should learn is actually to generalize this to lossy transmission lines. And to generalize this to lossy transmission line, I like to make this analogy. Okay, the analogy on the fact that if we were to put in loss in the transmission line, what we can do is that we can replace this capacitor with a leaky capacitor. This is not perfect. So when you try to charge this capacitor up, some of the currents will go through here and give rise to capacitive loss or leaky capacitor. And then if you have an inductor, the inductor is not made of a perfect conductor. So instead of when you're passing a current through it, the current will see a resistor as well. So there's some resistor loss or resistive loss. So if you want to introduce losses to transmission line, one need only to replace this topology with this topology, which is the same. The only thing is that this element here gets replaced by this element here. And this element here get replaced, or is replacing this element over here. We already know how to solve this problem. Okay, at least we know how to solve it in the time domain. But when you have to solve this in the time domain, it would be horrendously difficult. Because you know from the circuit theory course that when we have something like this, you better solve this problem using phasor technique. And in the frequency domain, they are actually topologically the same problem. Okay, so one way to solve this problem is actually to use the frequency phasor technique or frequency domain technique. and try to draw an analogy to this problem as much as possible. So what I want to say is that if you have this Telegrapher's equation in the frequency domain, or in the time domain, is given by this. Okay, maybe I should write out here so that I don't use the space I have here. Let me just write out here first. If I were to have this equation in the time domain, it will look something like this. And then but I know that I'm going to anticipate something very difficult if I insist on solving the problem using time domain technique, okay? I'm going to transform this into frequency domain. And if I do that, then I know that this will be something like z of omega partial z is equal to minus j omega L I of z of omega. Okay, let's assume that omega is a constant. Okay, and then the second equation would become diz of omega dz is equal to minus j omega c v z of omega. This is just a simple use of phasor technique. Okay, but now we have to deal with complex numbers. These are actually complex numbers. I'm not going to indicate them, but it's understood that they're complex numbers in the phasor world, okay? And then I noticed that the equation can be written more suggestively as dv dz. This is actually a impedance, okay? An impedance let me just write it like this. And then this would just be a inductance, okay? Let me see. If I write this as such, then it would be admittance, okay? This will be an admittance. The I, the Z will be minus, this will become Y. This will become Z, okay? So this is just Y of omega times V. Okay, so these equations in the frequency domain look very, very simple. And before I do that, I'd like to mention to you that this equation also look very simple in the frequency domain. And in the frequency domain, I can convert them into what I have there, but you also can write down the wave equation in the frequency domain, and they will look something like this. And then the wave equation in the frequency domain for the current will look something like this. Okay, I think all of you know how to do that because we have done that for the 1D wave equation before. But if you were to analyze this problem in the frequency domain, then you will say that the V, for instance, the V in the frequency domain will consist of two traveling waves, V plus e to the minus j beta z plus v minus e to the plus j beta z. These are all phasors now, okay? And then you can easily show that if you only have one wave equation, or you can only have one wave traveling wave, you can easily show that the ratio of this term, you can write down the corresponding one for the current. Plus I minus e to the plus j beta z. You can show that the first term is a traveling wave to the right, the second term is a traveling wave to the left. And you can easily show that if you were to repeat this in the frequency domain, you will show that the ratio of V plus to I plus is Z naught, which would be the square root of L over C, which is no surprise. I wouldn't show this, okay? Because the derivation is quite simple. You just plug it back in, you get this relationship. What is more important is that beta square is omega square LC, okay? This is just the analog of beta square to be equal to omega square mu epsilon for the wave equation, okay? But as I said before, the L and C is up for you to engineer. You can engineer transmission lines with different L's and different C's, okay, and hence different phase velocity. But if I were to generalize this to the case where this is arbitrary, and this is arbitrary, which is this case over here, okay, where my shunt conductance and my series impedance are arbitrary, I can immediately write down the pertinent equation for the arbitrary case, okay? Then what I should have is that if I go from the lossless to the lossy case, okay, Z is minus J omega L. In the lossless case, Y is equal to J omega C. This should be a plus here, sorry. And this is the lossless transmission line theory, which is for the bottom part. And if you want to write down the theory for the top part, you just let Z be equal to J omega L plus R. And then you just let Y be J omega C plus G. Agree? Okay. So because of the same topology and due to the mathematical homomorphism, I like to use this term homomorphism. Once you have the solution to the bottom structure, you can immediately write down the solution to the top structure. And then the same equation will still prevail, which is that in the frequency domain, the equation for the bottom structure is given by this. Okay. But what you need to do then is that if you want to generalize this equation for the top structure, you just do this replacement, okay, due to mathematical homomorphism. Can everybody see that? Using phasor technique or the frequency domain technique, one can solve the top structure quite easily and quite readily. Can everybody see that? Any questions? Or is this
for the second term, the change in I with shouldn't it be Y times V?
Maybe it's too simple for you. The wave equation, what is that? I hear a question. Can you say that again, please?
For the second equation, the di dz, shouldn't it be negative Y times V if it's the same form as the previous equation?
You mean this one over here?
Yeah.
The I dz is to the yi. The v dz is equal to, yeah, that's right. I have this messed up. Okay. Are they correct now? I hope they're correct. I have them correct up here. Okay. Yeah, they're correct up here. Okay, I have them wrong down here. Thank you for pointing that out. Okay. So now you can eliminate one of the two unknowns from these two equations and get the second order wave equation, which can be written in this manner. Yeah, thank you for pointing that out. At least I know at least one person is not sleeping, even though it sounds like a dead silence. Okay, so we have this equation, which is Helmholtz wave equation. Actually, it's Helmholtz equation, or the wave equation in the frequency domain. Okay, where now Z can be a complex number, not a pure imaginary number, but a complex number, a general complex number. Okay, and then ZY zy is equal to, as you know, the series impedance times the shunt admittance. Okay, this is shunt admittance. And then you can see that well, in general, it's a complex number. And if you were to solve this equation now, like dv dz square minus gamma square v equal to 0, okay, gamma square is zy, okay? And then what you have is that the general solution of this second order ODE is equal to e to the gamma z. So in general, the solution would be v plus e to the minus gamma z plus v minus e to the plus gamma z. Okay, the general solution would be this, and you can figure out what gamma is. Gamma is given by this equation, and in general will be a complex number. Gamma will have a real part plus an imaginary part. Okay. Any questions so far? So dealing with lossy transmission line is a piece of cake if you know how to apply phasor technique. And let's assume that we know how to deal with a transmission line in general. But what about if you want to do some engineering with transmission line theory? Okay, let's see what we can do. So let's discuss more transmission line theory. Okay. So let's assume that we have such a structure, a transmission line, and it will have a characteristic impedance Z0 given by this number. And this is up to you to engineer. And then you will have a velocity of wave propagating on it. It's given by this. It's again up for you to engineer. Okay. You can engineer this velocity that has different waves. And then let's assume that we have a wave traveling on this transmission line. So we draw this transmission line to be simple so that we can draw it easily in the classroom. But in general, it will have two waves traveling to the right and to the left. And then let's assume that we have a load, okay? And in general, the solution V of Z, let's not put in the omega dependence anymore. It's understood that there should be an omega dependence. And let's assume that we have the lossless case back again. Okay, for the lossless case, we know what beta should be. Beta should be this, which is actually the analog of this equation. Okay, that is the analog of that equation. And then we know that the wave will be reflected. The wave is traveling to the right. One of these waves is traveling to the right in the frequency domain. It looks like that. In the time domain, it will look like a traveling wave to the right. And then this one is traveling to the left. Okay, this is this term over here. This is that term over there. Okay, and let's do something with it. And let's assume that what is the relationship between the right traveling wave and the left traveling wave? Okay, let me just change notation a little bit. So what is the relationship between A minus and A plus? Okay, what is the relationship between them? And let's assume that we have a linear system to deal with. Okay, let's assume that this is known. One of this is known. This is not known. So we've set up this experiment that we know what the right traveling wave is, but we do not know what the left traveling wave is. Let's see if we can find the relationship between A plus and A minus. Okay, the way to do that is to mesh boundary conditions. The way to do that is to assume that the voltage at Z equal to 0. I'm going to use a different coordinate system here, okay? Z equal to 0 refers to the place where the load is. Okay, V at that point will be just equal to, in the frequency domain, the load impedance times I at Z equal to 0. Okay, that is what we know. So this is like a boundary condition of some sort. Okay, and we know that V Z is given by V plus e to the minus j beta Z plus V minus e to the j beta Z. And we impose the above boundary condition, and then we should have V at Z equal to 0 is V plus V minus, and that should be equal to ZL. And then I write down the expression for I do not have it written anywhere, but let me write it down anyhow. So it'd be V plus divided by Z naught e to the minus j beta Z minus, this minus sign is very important. Okay, V minus over Z naught e to the plus j beta Z. Why a minus sign there? The minus sign comes about because of the expression that we have previously derived. Let me go back and see if they can find that expression. Okay, I actually did not derive it. So here I just derived the expression for a right traveling wave. If you were to go through this exercise by assuming the wave to be left traveling, you find that there would be a negative sign out front here. Okay, I did not write it down, but if you go through this same exercise for a left traveling wave, you find that V over I is minus Z naught for left traveling wave. Okay, and the exercise is quite simple. You just plug them back into the transmission line, Telegrapher's equation, you'll find that this ratio is correct. Because of that, the ratio of the left traveling wave is having a negative sign. So I should put a negative sign there, okay? There's one thing I should do, which is that I'm going to assume that, let me go back to this. So I have this thing. So I at Z equal to 0 then would be V plus minus V minus divided by Z naught. Okay, if I impose this equation at Z equal to 0, I get this equation. And then I would have two equations and not two equations. I have enough equation to solve for my, let me see, the ratio, sorry, this ratio, V over I is equal to ZL, which means that if I take the ratio, okay, sorry, this should be I Z equal to 0. Okay, this is just V over I is CL, which means that V plus V minus divided by V plus minus V minus times Z naught. I divide this equation by the second equation, I get this equation. And then if I were to solve for V minus, I could easily do it, but let me be a little bit clever and say that V minus should be linearly proportional to V plus, because this is a linear system, okay? V minus should be linearly proportional to V plus, and if I do that, then V over I, and if I put this substitution into here, I will get 1 plus gamma L, V plus divided by 1 minus gamma L, V plus times Z naught. Okay, I have a Z naught out there. The V plus cancel each other. I have V over I at Z equal to 0 should be ZL, should be 1 plus gamma L over 1 minus gamma L times Z naught. So this is another important transmission line formula. Okay, this formula says that once you know the load impedance at the far end, at one of the ends of the transmission line, that you can define a gamma L, and gamma L is related to ZL in this manner, okay? And that you can invert this equation and say that I can have a normalized load, which is ZL over Z naught, and that would be 1 plus gamma L over 1 minus gamma L. You can invert this equation. It says gamma L is Z and L plus 1. Okay, you can invert this equation very easily and get this. So this equation allows you to go back and forth between the load impedance and the reflection coefficient. This is called the reflection coefficient. This is a normalized load impedance. Normalized load impedance. And this allows you to go back and forth between them. And these two formulas are very, very, very important in transmission line engineering. Okay. Let's look at some of the ways of solving this equation. So for the lossless case, it is rather simple, but most of the time we don't have to deal with loss so much. So we are okay with just playing around with the lossless case. So one of the things is that, well, with this thing in mind, then we know that VZ is V plus e to the j beta z plus gamma L e to the plus j beta z. And this is general formula for the V on the transmission line. And then you will have this being equal to V plus over Z naught e to the minus j beta z minus gamma L e to the plus j beta z. Okay, so the voltage and the current on the transmission line is now easily written down. Okay, we start off with VZ being equal to this over here. We know how to find V minus in terms of V plus, V minus in terms of V plus. We just relate it by the reflection coefficient. You plug this in, you only have this term on the first line. And then you can write down the formula for the current as well. The formula for the current will look something like that. And then again, you substitute in V minus with this relationship. And taking note of the minus sign, the second expression has the minus sign out front over here. So the voltage and the current are given by these expressions over here. What this says is that the voltage and the current are not constant. They're not constant on the transmission line, because when you have an incident wave coming in, it gets reflected, and the gamma L is equal to Z plus 1. I think we just derived this. Okay, we just derived this. The Z normalized load is ZL over Z naught. This is called the normalized impedance. Okay. What thing that you should notice is that this voltage and current are not constant. The reason why they're not constant is because there is an interference of the two waves on this transmission line. The left wave and the right wave are not in phase. Not in phase because they're represented by two very different looking mathematical expressions. So there are no phases that cancel. And in general, this VZ over IZ is rather complicated expression. And if I plug that in, I will have something that looks like this, okay? Z naught the V plus would cancel, and then I will have something that looks like this, plus gamma L e to the plus j beta z over gamma L e to the j beta z, okay? But this expression is still not good enough for many of us. And we tend to re-manipulate this expression into a form that is easier for us to remember. And that form is, let me take this factor out and take this factor out in the numerator and denominator. And then what I have left in the numerator would be something with the 2 j beta c. And then in the denominator, I will have the same thing, but with the minus sign there, but with the factor of 2 j beta c. And in most textbooks, you will see this formula being used rather than the one that is above, okay? And the reason why this formula is preferred is because it looks like a previous formula that we have derived, okay? We have derived this formula. I don't know if you still remember that. This formula has the same structure as this formula, 1 plus something, 1 minus something. This formula also has something. So we can call this the generalized impedance because it will have a unit of impedance. And because of its close parallel to this formula. So it's good for remembering. If you remember this formula, you should commit to memory if you're a microwave engineer, okay? Then you can go back and forth between these two formulas. Once given the impedance, you can find the reflection coefficient. And once given the reflection coefficient, you can find the impedance, okay? So microwave engineers love this formula because they can go back and forth between them very easily. Reflection coefficient and impedances are the same thing, okay? So this is very important for microwave engineers, and so let's see what we can do with them. Well, let's assume that this impedance is the ratio of the voltage and the current at any given point in space, and this is not a constant anymore, okay? So if you would look at one special case where I have a load, but the load is very special. The load is very special. And I can look at the case where the load ZL is 0. That means I have a short circuit. Okay, if I have a short circuit, then I can put 0 into this formula here. Okay, I can put 0 in. There's a way of going back and forth in this formula. And then you would have, the way of going back and forth between them is that ZL is 1 minus gamma L over 1 plus gamma L times Z naught. And then gamma L is 1 plus Z, it should be the other way around, I think. Z normalized load over. Okay, you have to go back and forth between these two formulas very easily, and you should know them like the tip of your fingers. Okay, so if I look at this formula now, if I have a short circuit, ZL equal to 0, then gamma L, what is gamma L then? Remember that ZNL
Should be 0.
not really. Let me, can you hear me? Because I just get the signal saying that my internet connection is poor. Okay. Remember that ZNL is just ZL over Z, the normalized impedance. So if ZL is 0, ZNL would be 0. And if ZNL is 0 in this equation, what is gamma L? Not 0. Somebody utter 0.
1.
1, very good. Okay. No, not 1. 1 is not the correct answer. I jumped too quick to the conclusion. If you have a short circuit, what is the reflection coefficient?
-1.
-1. Good. Somebody got it. Wonderful. Okay. And if you have a short circuit gamma L is -1, then I can go back to this formula and look at this formula again, okay? Gamma L is -1, and this formula becomes somewhat simplified, not completely simplified because numerator is still not constant, still not canceling the denominator, okay? And you can go back and work out this formula. I like to say that this formula has been worked out by very many microwave engineers for this particular case that we are interested in. Okay, the particular case that we are interested in. And if you know the impedance at this end, what is the impedance at this end? Okay. Thanks to all our predecessors of microwave engineers, the formula is that Z at -L, which is at Z equal to -L location. And that formula is, you can go through trigonometric algebra, okay, and arrive at this formula. I say that if you're not a microwave engineer, you do not have to commit this formula to memory. Okay, if you're a passerby learning this field, just remember that there's a way to get back and forth between ZL and the impedance at -L. Beta is the wave number of the, okay. So the reason why I want to write this formula down is because I want to use it for this problem over here, where I have a short. And if I have a short, I go back to that formula, I will find that Z minus L would just be J Z naught tangent of beta L. Okay, tangent of beta L. You can either work out using that formula that we have derived, or using this formula where a lot of microwave engineers would have committed this to memory. They will put ZL equal to 0 here. And then ZL equal to 0, and then this Z naught cancel with that Z naught, and then you can get this simplified formula here, okay? And now with this formula, what it says is that the impedance is not a constant on a transmission line. Even a simple transmission line like this, and that impedance will look something like this, okay? If you were to plot the impedance, it will look purely inductive because it looks like a pure imaginary number. And it actually grows to be a very large value if the length of the transmission line happens to be pi/2, okay? Or if the transmission line happens to be a quarter wavelength. If you have a short circuit here, if you move yourself backward to a quarter wavelength away, you see an infinite impedance. And then if you move slightly beyond that, the impedance would flip sign. Okay, the inductance becomes negative infinity. And then it goes back to 0 and then becomes positive. So this part of the transmission line, we call the transmission line to be inductive. And the other part of the transmission line, we call it to be capacitive because of the signs of the admittance. Remember that in your circuit theory course, Z equal to J omega L, and then Z equal to 1 over J omega C. This is minus 1 over omega C. Okay, so a capacitor has a negative reactance. Okay, if you relate this to Jx, relate this to Jx, then a capacitor has a negative reactance and inductor has a positive reactance. So the wonderful thing about transmission line theory is that you can make both capacitance as well as inductance out of them because of the interference effect of the two waves. You just need the two waveforms. They interfere with each other. They create a standing wave or interference wave. Okay, in this case, it's actually a standing wave, okay, because the two waves are just almost in phase or in phase with respect to each other. You get a standing wave, and by using the interference nature of the standing wave, you can get capacitances as well as inductances out of them, okay? And then we can go to the other case. This case is when we have this same figure. Let me see if we can copy it. Same figure. Okay, I don't want this. Close this. So now if you replace it with a open circuit, ZL, okay, instead of being 0, you will go back to this same formula that we have derived, or the microwave engineers have derived, hardworking microwave engineers, and you let ZL being going to infinity. Then this term would be the dominant term in the denominator. This one would be the dominant term in the numerator. Then you have something that looks like 1 over tangent. It becomes a cotangent, if you remember your trigonometry well. Okay, 1 over tangent becomes a cotangent. And what you have is that the formula now actually looks something like, I don't have it written down anywhere, but I'm sure that you can figure that out too. And we can figure that out very quickly. And that if it's a open circuit, then Z minus L is equal to minus GZ naught. I think that's correct. Cotangent of beta L, okay? And it just becomes this, which means that when L is very small, it is a capacitive thing. Okay, it means that if you have an open circuit, if you look here at this end, it looks capacitive when the length of this transmission line is very short. Okay, and then it becomes inductive and then capacitive and then inductive again due to the interfering nature of the two traveling waves on this transmission line. And this is very important for microwave engineering. And one take-home message here that you should get is that, when you have a short circuit, like we have here, when you have a short circuit at one end of the transmission line, and if you look here, and when the length of the transmission line is very short, it looks like an inductor. It is a take-home message. Why? Because when it is a short circuit, if you drive this system with a voltage, you get huge current flow. The huge current flow gives rise to strong magnetic field. A magnetic field means a strong inductor, okay? Whereas if you have an open circuit, okay, if you drive this with a voltage source, the current cannot go anywhere, so they start to build up charges on this transmission line. And when you have charges, you have electric field that looks like this. It becomes like a capacitor. Okay, this is the good take-home message between a short-circuited transmission line and open circuit transmission line. Okay. Well, why is this so important? Well, these are very important things to microwave engineer, especially this formula. Gamma is Zn minus 1 over Zn plus 1. Okay. Zn is 1 plus gamma L, 1 minus gamma L. Okay. And microwave engineers need to solve these two equations rapidly with a snap of their fingers. They want to get an answer. And at the time, they don't have calculators, no calculators like you guys do. Okay. Moreover, Zn and gamma can be complex numbers. So what do you think they invent? What do they invent? If you're a good microwave engineer during that era, before you had calculators, and you need to solve these two equations over and over again.
Maybe some table of values.
You can use tables of values, but microwave engineers are cleverer than that. Okay, can anybody think what they have come up with?
Maybe some chart.
Or you use charts, Smith charts. Okay, they're very clever. You use the Smith chart. I guess it was introduced by Mr. Smith sometime in the 60s or something. So this is a Smith chart. A Smith chart is a map between the impedance complex plane. You have to know complex variables to appreciate this deeply. Okay, the left is a value of all possible impedances on the complex Z plane, okay, or impedance plane. The right is the map of all possible reflection coefficients on the gamma plane. If you know complex variables, you will call these two planes Z plane and gamma plane. And then you can just draw a map, one-to-one map. This is called one-to-one map. And this map is bilinear. Okay, it's based on this formula that I have shown before. Okay, these are called bilinear transforms. And their property that you learn from complex variable the bilinear transforms map circles to circles. So what you can think on the left-hand side is that you have pictures of a circle with infinite radius. Since these are bilinear transforms, those infinitely large circles are mapped into finite size circles on the right-hand side. This line will map to this line will map to that line, okay? And then this horizontal line, which can also be thought of as an infinitely large circle, maps to this line over here. You can think of this as being forming a circle over here. This other line forms a circle, something like that over here, okay? So why is it so wonderful? Well, this is something where the Smith chart can be constructed. That means that if you're a microwave engineer, you carry one of these charts around with yourself. You put them in your pocket or put them in your sleeve pocket or somewhere, okay? They are even better than a calculator. So what you do then is that you read off the left-hand side with an impedance value, and then if you know how to read off the impedance value, you can immediately get the reflection coefficient using this chart, or vice versa. If I give you the reflection coefficient, you put that dot on the reflection coefficient here. It's a complex number, and then you can read off the impedance value. Does everybody get it? Is this confounding to some of you, or you have to sit back and think about it, meditate on it, and it actually is a wonderful device.
I have a question.
Sure.
The values of impedance and values of reflection coefficients on this chart.
Right. Right. So you read them off, just like you read them off over the chart over here. Okay. These are the gamma plane, which is the plane of the complex reflection coefficient. This is a plane of the impedances, but this has been mapped to this circle on this chart. So this is like the real axis maps to this line over here. This line over here maps to a line that looks like this. This other line maps to this line. So you can sort of see the Cartesian coordinates being mapped onto this circle. Okay? Infinity gets mapped to some value over here. And then zero impedance, which is this point, gets mapped to this point over here. Okay, did that answer your question? What was the question you wanted to ask?
Yes, this was my question was.
Yeah, you have to sit down and meditate on it. It's a wonderful gizmo for microwave engineers to use, okay? And then you can talk about standing wave ratio, which I don't have time to talk about, because what happens is that on the transmission line, the two waves are not in phase. The right traveling wave and the left traveling wave are out of phase with respect to each other. They give rise to interference wave pattern on the transmission line. And you can work out the interference wave pattern using a diagram like this, 1 plus gamma, 1 minus gamma, because the current, the total amplitude will be proportional to this length, and as you move around, this thing you see that the amplitude is not a constant, okay? So you have things like, you see an interference pattern on the transmission line. And by measuring the interference pattern using a device, which is out of fashion now, because everything is done electronically. If you are in a microwave engineering lab, you can hardly see this device. Okay, this is called the, what is it called? A slotted line. Okay, a slotted line is a waveguide with a slot in the middle. You can measure the voltage in the transmission line. And this is another setup you can actually use to measure this standing wave ratio. And from that standing wave ratio, you can actually go back and forth between the voltage standing wave ratio and the reflection coefficient. Because as you can see from here, that if you know the standing wave ratio, if you know the standing wave pattern, if you know the standing wave, let's go to this slide to explain the point. If you know the standing wave pattern of this voltage and current, you can figure out what the reflection coefficient should be. And vice versa. If you know the reflection coefficient, you can figure out the impedances, okay, from the Smith chart. So measuring the standing wave ratio is an important endeavor in a microwave engineering laboratory. Okay, I think I'll stop here unless you have any questions. Because this part of the course is usually like a revision for many of you if you have taken an undergraduate electromagnetic course, because these mathematics, they are rather simple, and they actually are being taught in many schools. And if you do not have an undergraduate course where this has been taught before, you can read my 350 notes, okay? Lecture notes. Okay, and then you can understand transmission line theory quite well. And if you have any question, you can ask our teaching team, the TAs, the assistant instructor, and me, okay? You can catch me, okay? This afternoon, I will not be holding an office hour because I have another final exam to attend to. So Dr. Na would be the one who would be giving the office hour this afternoon. I'll let you go, unless you have any other questions. Okay, I'll see you next week then.
Professor Chu?
Yes, sure.
When could we expect the exam to be emailed tomorrow? What do you know?
Yeah,
what time?
I email it out tomorrow. I'm still thinking about it. Okay, so
Okay.
I'll formulate the problem either tonight or tomorrow and email the problems to you.
Okay, thank you.
Okay. Okay, enjoy yourself. Be safe. Don't go partying because you can't. Otherwise, you will fail your take-home exam. Okay. Bye-bye.
Thank you.
Sure.